Okay, so the last couple of days we've been talking about ions, right? We've been talking about cations, which are what kind of charge? Positive, and anions, which are what kind of charge?
Negative.
Negative, and then we learned about something called a polyatomic ion, which is what? A group of atoms that are charged, right? Usually negatively charged. There are a few positive, but most of them are anions, okay? Now, this is leading us up into our discussion on ionic bonds and ionic compounds, because ionic bonds and ionic compounds are made up out of ions. Okay. Ionic compounds are composed of two parts. You have to have a cation part and you have to have an anion part. Usually cations are a metal, sometimes hydrogen. Usually anions are nonmetals or are polyatomic ions that we just learned about, right? But for the most part, when you are trying to identify an ionic compound, 95% of the time, if you have a metal and a nonmetal, you're ionic. Okay. Another name for an ionic compound is something called a salt. Table salt, which is what you guys are most familiar with, actually is a type of salt, but it's not the only salt. So in chemistry, when I say salt, I'm not necessarily talking about table salt. Okay. Table salt is made out of sodium and chlorine. Sodium is an alkali metal. Chlorine is a halogen. Stick those together, it makes a salt. But lithium and fluorine, also an alkali metal and a halogen, also make a salt. Okay, salt is just a way of saying you have a metal and a nonmetal bonded together ionically. Another thing about ionic compounds is they are electrically neutral. Now, when I say neutral, in this context, what am I meaning? Yes? Almost. Okay, she's almost there, right? She's almost there. Usually up to now when we say neutral, we're talking about equal number of protons and electrons, right? But now we're going to tweak that just a little bit. When we're talking about compounds, we're actually talking about the charge of the ions being equal and opposite. So like for instance, sodium chloride, sodium has a charge of +1, chlorine has a charge of -1, +1 -1, what does that equal? 0, so is that neutral? Yes. Okay, the positive charges have to equal the negative charges. Okay, if they don't, then we have to change the ratio to make them equal. Okay, so a few more characteristics of ionic compounds. First of all, ionic compounds have something called crystalline structure. Now that sounds complicated, but it's really not. Crystalline structure just means it looks like a crystal. If you don't know what a crystal looks like, think about a diamond, think about jewels, think about any sort of ring, necklace, okay? Crystalline structure means a crystal. Has anyone ever actually looked at a piece of salt, like closely? Is it round? No. Kind of cube-like. It has flat edges, okay? This means it's a crystalline structure. Just like diamonds have flat edges, so does salt. Why? They're ionic compounds. They have crystalline structure. Now, ionic compounds also have high melting points, which means what state of matter are they usually in at room temperature? Solid. You have to be at a really high temperature to melt, then you're probably most likely going to be in solid form, right? And then the last property that I like to talk about with ionic compounds is they can conduct electricity when they are dissolved in a liquid. For example, salt water. Now, the most popular misconception is that water conducts electricity. Does water conduct electricity? No. Water is a covalent compound. It does not conduct electricity, ever. So if water does not conduct electricity, why are there warnings on your hair dryer telling you not to stay in the bathtub and dry your hair at the same time? Why? But if it doesn't conduct electricity,
why does it go through it?
Then how does that work? Why? Because do you think what comes out of our tap is pure water? No. It has stuff in it. How do we know that it has stuff in it? Around here, we have limestone in our bedrock, right? So as water goes down through the ground, it dissolves our limestone, which is calcium carbonate. So when it comes out of our shower heads, it comes out usually as hot water. So the water evaporates, leaving behind everything else, which is why you see the white buildup on your shower heads and on your sink faucets. That white buildup is actually calcium.
It was just water itself, electricity would go through.
If it was just water, pure water, nothing in it, it would not conduct electricity.
So if you were like taking a bath in distilled water, you could like just be on your laptop chilling.
Yep. Theoretically, I wouldn't try that, but yes. The idea, getting 100% pure water is pretty difficult because there's so much stuff in water. But you can buy, she just said you can buy deionized water at Walmart. I still don't know if I would trust that it's 100% water. Still probably some degree of stuff in there. But yes, I have some deionized water back there. Maybe tomorrow I'll pull it out and I'll bring out a electricity meter and let you guys see that it's really not conducting electricity. All right. So now let's start talking about ionic bonds. So ionic bonds hold together ions by something called an electrostatic force. Now, electrostatic force is really not that scary of a word. An electrostatic force just means that there is an attraction based on the charges. I always like to compare them to magnets. If you have a North Pole magnet and a South Pole magnet, what's going to happen? They start to stick together just because they have opposites, right? Same thing with ions. Ions are attracted to each other without any energy being used because they have opposites in charges. So, let's do an example now. We're going to use the example of sodium chloride. I'm just going to beat salt into the ground today. Sodium has one valence electron. How do I know that? It's in the first column, first group, right? The first group, all of them have one valence electron. Chlorine has 7 valence electrons, right? How do I know that? He's in the 7th column. So, when I try to draw their Lewis dot structures, sodium's going to get 1 dot, chlorine's going to get 7 dots, right? Now, following the octet rule that we talked about the other day, the octet rule means that elements want to have 8. Sodium has 1. Do you think he's going to lose 1 or gain 7? Lose 1. Chlorine has 7. Is he going to gain 1 or lose 7? Gain 1. Sodium wants to lose 1. Chlorine wants to gain 1. Win-win situation, right? So sodium is going to give chlorine his electron. And so now sodium's electron is no longer around sodium, it's around chlorine. So sodium is now going to be charged. Chlorine is now going to be charged, but they are going to be oppositely charged, right? So sodium's +1, chlorine is -1. Yay, everybody's happy, right? And they are now stuck together in an ionic bond because they have opposite and equal charges. But this is a pretty easy example. Why is this a pretty easy example? Because it was a 1-to-1 ratio. Sodium had 1 to lose, chlorine needed 1, easy peasy. Let's look at a little bit more complicated one. Let's look at calcium and phosphorus. Calcium has 2, he's in the 2nd column. Phosphorus has 5 because he's in the 5th column. What do you think calcium's going to want to do? Lose 2. What does phosphorus want to do? Gain 3. Lose 2, gain 3. That's not as easy, is it? So what's going to happen is calcium is going to give phosphorus his 2 electrons. Yay. Now calcium's happy, right? Is phosphorus happy though? Nope. Phosphorus isn't happy, so we need an additional cation, don't we? We need to add another cation to make phosphorus happy, so we throw in another calcium. Well, phosphorus only has 1 more spot. Calcium wants to give away 2. So he's going to give phosphorus the 1. So yay, now phosphorus is happy. But the second calcium's not now, right? So we're probably going to need an additional phosphorus. So now calcium's going to give phosphorus that 1 that he has left. So yay, now he's happy. But is phosphorus happy? No, so we probably need another calcium. So what do you think this calcium's going to do? He's going to give both of them away. Yay, everybody's happy now. So sometimes we have to keep going back and forth. It's kind of like a give and take. Eventually, all your electrons will work out. Eventually, everybody will be happy. But sometimes it does take a little bit to show. So, if I had to write the chemical formula for this guy, all you do is you count up calciums, you count up phosphoruses. So how many calciums do I have? 3. So that's going to make it Ca3. How many phosphoruses do I have? 2. Phosphorus, 2. So this is going to be Ca3P4. Now, if I ask you to name this guy, I bet you guys can figure out what the name of this is without me even telling you. First of all, what is the name of this ion? Calcium. Do cations' names change? What is the name of this ion? Phosphide. So therefore, the name of Ca3P2 is calcium phosphide. Done. This isn't so bad, right? Now, does this compound get a charge like our polyatomic ions did? No. Why does this compound not get a charge? Because this is technically plus 6, right? This is minus 6. Plus 6 minus 6, what's that equal? 0. So is he neutral? Yes, so we don't need to put a charge on him. All right, so let's do another example. Now, luckily for you guys, ionic compounds, you don't have to draw the structures. You don't need to draw the Lewis dot structures for an ionic compound because we don't need to look at that. We can look at the periodic table. We can figure out charges based on where they are on the periodic table. So why don't we just skip that step and save ourselves a little bit of time, right? So now we're going to do another example, and we're actually going to do an example between magnesium and chlorine. So the easiest way that I always tell you guys to do is write down the ion form. So, okay, write down magnesium. Then you write down chlorine. Then you use the periodic table to determine their charges. Magnesium's in the second column, so what kind of charge does he have? 2 plus, 2 positive, right? Chlorine's in the 7th column, so what kind of charge does he have? He's in the 7th column, which means he has 7, so he's going to gain 1. So what's his charge? 1 minus. So the easiest way, we don't need to draw anything out. Write the ions, and then you take the number of the charge and you cross them. So the chemical formula for magnesium and chlorine is going to be magnesium Cl2. Done. Easy, right? You write down the charges, you take the number, and you put them with the opposite element. Chlorine has a 1 charge, so the 1 goes with the magnesium. Magnesium has a 2 charge, so the 2 goes with chlorine. So now let's see if we can name him. So again, you name the cation first. So what's the name of our cation? Magnesium. What's the name of our anion? Chloride. And we're done. You guys ready? You want to do another example? I think so. All right. So let's figure out the chemical formula and the name for a compound between bromine and aluminum. So what do you think my first step is going to be? I need to look up the charges. So if I look up at the periodic table, and luckily for you, I wrote all the charges on the periodic table for you. What is the charge of bromine? -1. What's the charge for aluminum? +3. So now what you do is you take the number on the charge and you give it to the other element as a subscript, right? So we're going to need 3 bromines for every 1 aluminum, but I put these out of order for a reason. Who always goes first? The cation. So I'm going to write it as aluminum Br3. What's the name of this guy going to be? Aluminum bromide. This isn't so bad, right? But, uh-oh. There's a little and, if, or but when we're naming ionic compounds. Those pesky transitional metals. They don't like to follow the rules. So, the other day we talked about the charge of transitional metals. Transitional metals do not always have a specific charge. Does anyone remember why they don't have a specific charge? Has to do with their orbitals. Right. Transitional metals already have full s and p orbitals, so they are already following the octet rule, so obviously they can't continue to, that's not going to be their determining factor. Transitional metals are more concerned with their d orbitals, and they want them to be half filled or filled to increase their stability. So we can't look at the periodic table and determine the charge of a transitional metal. Not only can we not determine it from the periodic table, but transitional metals sometimes have more than one possibility. For instance, iron can exist as +2 or +3. Manganese can exist as +1 or +2, so on and so forth. The transitional metals can often exist in more than one form, so we need some sort of way to differentiate between the forms when we name them. It's a really easy way. We just put the charge as Roman numerals after the name. So for instance, like if I was dealing with copper with a 2+ charge, I would name him copper. Oops, wrong one. I would name him copper. And then I would put, after copper, in parentheses, I would put the Roman numeral, oh my gosh, 1. Okay, I know it's a little hard to read. I'll fix that on the next slide. Alright, so you guys want to do a couple examples of those? Sorry. Okay, so let's choose, I don't know. Let's do orange. I'm in an orange kind of mood. Yes. Oh. Okay, what is the chemical formula and name for ionic compound with iron 2+ and chlorine? So I'm telling you iron is a transitional metal. Which form of iron am I dealing with? The 2+ form. So we're going to do the exact same thing as we've done before. We're going to write our ions down. So we have iron with a 2+ charge, right? We also have chlorine, which we have to look up. What kind of charge does chlorine have? 1 negative. So you cross the numbers, right? What's our chemical formula going to be? FeCl2. Which, this is no different than what we've been doing, right? The only different part comes to when we name them. So when I write the name of this guy, he is going to be iron, parenthesis, 2, chloride. Now, oftentimes when it comes to the test, when you see this, your brain wants to go, oh, I have 2 irons. But that is not what those Roman numerals are meaning. Those Roman numerals are telling you that iron has a +2 charge. Okay, so now let's look at the second example. The second example wants us to do the same thing for iron 3+ and oxygen. So, iron 3+, different form of iron, right? Oxygen has what kind of a charge? 2 negative. We cross the numbers. What's our chemical formula? Fe2O3. And the name of this guy is going to be iron. In parentheses, we put a 3. And then oxide. So this isn't too bad, right? It's really not too bad. It's pretty straightforward. There's really not a whole lot of wrenches to throw in there except for transitional metals. That's the only thing that we kind of have to watch for. You have a little bit of homework on the website. It's in the homework section. It's titled Ionic Compounds. It's not actually due till Monday, but I do want you to go ahead and get started on it now because you will have a little bit of homework tomorrow night as well. Okay?
Okay, now go back to that one.